You've decided to do something no human has ever done. You're going to fall into a black hole. What happens next depends on one thing: which type of black hole you're falling into. Fall into a small stellar black hole. You die before you even reach it. Fall into a supermassive one, and the experience becomes something far stranger. Today we follow the stranger path, a supermassive black hole. Strap in. This is going to get weird. First, the event horizon. This is the boundary, the point of no return. Cross it, and nothing, not even light, can bring you back. But here's what makes a supermassive black hole so strange. As you approach it, you feel nothing unusual. According to physicist Glenn Starkman of Case Western Reserve University, a freely falling astronaut approaching a supermassive black hole may cross the event horizon without noticing anything particularly special. You are now inside, and the universe outside has just become unreachable. Forever. Now, while you feel completely normal inside, something extraordinary is happening to you from the perspective of someone watching from outside. According to Einstein's general theory of relativity, time passes more slowly in a gravitational field. The stronger the gravity, the slower time moves. From the observer outside, they see you slow down. You appear to freeze, like a statue, just at the edge of the event horizon. But you, falling in, experience time completely normally. Your watch ticks normally. This is one of the most mind-bending results of Einstein's relativity. Two observers, same event, completely different experiences of time. Both are correct. This has been verified experimentally here on Earth. Atomic clocks placed at the top and bottom of tall buildings show measurable differences in the passage of time. Because even Earth's weak gravity produces time dilation. Near a black hole, this effect is amplified to the extreme. At the event horizon of a black hole, this effect is so extreme that time, as seen by the outside observer, appears to stop completely. But remember, inside the black hole, you are still moving, still falling. And now, something else begins. As you fall deeper, the gravity pulling at your feet becomes stronger than the gravity pulling at your head. This difference in gravitational force, called a tidal force, begins to stretch you. Your feet accelerate faster than your head. His process has a name, coined by the legendary physicist Stephen Hawking in his book, A Brief History of Time. It is called spaghettification. Your body is being stretched vertically like spaghetti dough and compressed horizontally at the same time. According to physicist Farr of the University of Oregon, this would likely happen within just a few minutes of crossing the event horizon. His stream of what was once you, now a thin ribbon of atoms, rushes toward the center at nearly the speed of light. From outside, this entire process looks like slow motion. You appear to freeze and fade at the event horizon, and the thin stream of atoms that was once you reaches the singularity, the center of the black hole. According to Einstein's equations, the singularity is a point of zero volume and infinite density. Every bit of mass that falls in gets compressed into this impossibly small point. And here is where science hits a wall. Our best theories, general relativity and quantum mechanics, completely break down at the singularity. We simply do not know what happens at the singularity. It is the boundary of human knowledge. In 1974, physicist Stephen Hawking theorized that black holes are not truly permanent. They slowly emit energy, now called Hawking radiation, and over an almost incomprehensibly long time, they evaporate. And this creates one of the deepest unsolved questions in all of physics. If everything that fell into the black hole is destroyed when it evaporates, what happened to all that information? This is called the black hole information paradox, and as of today, it remains unsolved. Even Stephen Hawking, Albert Einstein, and the greatest physicists alive today have no complete answer. So, what happens if you fall into a black hole? You cross an invisible boundary without feeling it. Time itself bends around you. You are stretched into a cosmic noodle. You hit a wall where physics breaks down completely, and the universe may never know you were there. Black holes are not just objects in space. They are questions, wrapped in darkness, pulling at the edges of everything we think we know. And speaking of questions, have you ever looked up at the night sky and wondered, are we alone? Because in our next video, we're going to talk about the Fermi paradox. The universe is 13.8 billion years old. It has hundreds of billions of galaxies, each with hundreds of billions of stars, and yet, complete silence. No signals, no visitors, no proof of anyone else. Where is everybody? Subscribe so you don't miss it. It might be the most unsettling video we make. See you in the next one.